For 12 years, scientists waited for these images. Not because they expected another beautiful picture of space, sharper galaxies, brighter nebulae, or a new wallpaper for astronomy enthusiasts. They were waiting because these images represent the first pieces of a cosmic map unlike anything humanity has ever attempted to build. It is a map of billions of galaxies, stretching across nearly 10 billion years of cosmic history, designed to reveal something we cannot see directly, cannot touch, and still do not fully understand: dark matter and dark energy, the invisible components that appear to shape the structure and evolution of the universe. On July 1, 2023, the European Space Agency's Euclid Space Telescope was launched from Cape Canaveral toward the Sun-Earth Lagrange Point 2, L2, approximately 1.5 million kilometers from Earth. This is the same stable gravitational region occupied by observatories such as the James Webb Space Telescope in Gaia. After years of development, testing, and calibration, Euclid began returning its first scientific images, and what astronomers saw was both breathtaking and scientifically significant. Among its earliest observations were galaxies hidden behind the dense foreground of the Milky Way, more than 630 previously unknown dwarf galaxies within the Perseus cluster, a globular cluster captured in extraordinary detail after only a short observation, stunning views of the Horsehead Nebula revealing numerous previously unseen features, and the first pieces of a three-dimensional cosmic atlas that could help scientists understand how the invisible universe holds everything together. These are the observations researchers spent more than a decade preparing to obtain. They may fundamentally improve our understanding of the universe's structure, its evolution over cosmic time, and the hidden framework created by dark matter and dark energy. Unlike most space telescopes, Euclid was not designed to focus on individual galaxies or isolated astronomical objects. It was built to map the universe itself. Its mission is among the most ambitious ever undertaken in astronomy: to construct the largest and most precise three-dimensional map of the cosmos ever created. During its 6-year mission, Euclid will survey an enormous portion of the sky, measuring billions of galaxies across vast distances, including galaxies whose light has traveled for more than 10 billion years before finally reaching its instruments. This mission is about far more than measuring distance. It is about looking backward through time. The farther Euclid observes, the younger the universe appears. It sees galaxies during their early stages of evolution, galaxy clusters still assembling, and the immense cosmic web still taking shape. By comparing galaxies observed at different distances, and therefore at different moments in cosmic history, astronomers can reconstruct how the universe evolved over billions of years. This is why Euclid is so important. It functions not only as a time machine but also as one of humanity's most powerful tools for studying gravity itself. The universe we can see represents only a small fraction of what actually exists. Galaxies are not distributed randomly throughout space. Instead, they gather into clusters, stretch along enormous filaments, and form an immense cosmic web extending across the observable universe. Something invisible appears to guide this architecture. That unseen influence is believed to be dark matter, which exerts gravity despite emitting no detectable light. At the same time, another mysterious component, dark energy, appears to be driving the accelerating expansion of the universe. Together, dark matter and dark energy account for the overwhelming majority of the universe's total contents, yet their true nature remains one of modern science's greatest mysteries. Euclid was specifically designed to investigate these invisible components through two complementary techniques. First, its high-resolution visible light camera measures the shapes and positions of galaxies with extraordinary precision. Tiny distortions in the apparent shapes of distant galaxies reveal the effects of gravitational lensing, the subtle bending of light caused by massive objects lying between those galaxies and Earth. Even when that intervening mass consists entirely of invisible dark matter, its gravitational influence leaves measurable fingerprints in the distorted light. Second, Euclid uses its near-infrared spectrometer and photometer to measure the redshifts of galaxies, allowing astronomers to determine not only where galaxies appear on the sky but also how far away they are. The result is a true three-dimensional map of the cosmos rather than a flat image. This enables Euclid to chart where galaxies are located, how they cluster together, and how invisible matter may be shaping the universe's largest structures. The mission is effectively constructing a detailed map of cosmic depth, revealing both the visible galaxies and the hidden gravitational framework that organizes them. The first images immediately demonstrated what makes Euclid unique. It combines an exceptionally wide field of view with remarkable image sharpness, allowing it to capture enormous cosmic structures while simultaneously preserving fine details within individual galaxies. It can observe both the forest and the leaves at the same time. That capability is precisely what astonished astronomers. Even within its earliest observations, Euclid was already revealing objects and structures that had remained hidden in regions of the sky researchers believed they already understood. One of Euclid's first major scientific targets was the Perseus cluster, located approximately 240 million light-years from Earth. At first glance, the image appears to be an overwhelming sea of galaxies. More than 1,000 galaxies belong to the cluster itself, while over 100,000 more distant galaxies fill the background. Yet this image is far more than a spectacular photograph. It serves as a laboratory for studying gravity on the largest scales. The galaxies within clusters such as Perseus are not scattered randomly through space. They occupy positions determined by gravity,